Hi everyone, I'm guessing you're here because you need some help on this question. Lucky for you, I'm here to give you a tutorial. This is from the College Board AP Chemistry exam from 1995, free response, question number 1, letters A through E. It's a question on equilibrium, and equilibrium is very tricky. So let's get started. All my work's going to be done on a separate sheet of paper, so don't worry if you don't see it on here. The question reads, when hydrogen gas is mixed with carbon dioxide at 2000 Kelvin, equilibrium is achieved according to the equation above. In one experiment, the following equilibrium concentrations were measured. Hydrogen gas, 0.20 molar. Carbon dioxide, 0.30 molar. H2O gas and carbon monoxide, 0.55 molar. Question A asks, what is the mole fraction of carbon monoxide in the equilibrium mixture? So what you're going to do is you're going to take 0.55 molar, which is the molarity of carbon monoxide, and you're going to put that over 0.55 plus 0.55 plus 0.30 plus 0.20, which is the combination of all four concentrations, and you're going to get 0.55 over 1.60, which is the combination of this. Then you're going to divide 0.55 by 1.60, and you're going to get 0.34. Multiply that by 100, and you're going to get 34% carbon monoxide in the equilibrium mixture. Now for question B. Using the equilibrium concentrations given above, calculate the value of Kc, the equilibrium constant for the reaction. To calculate the equilibrium constant, you put concentration of products over concentration of reactants. So we're going to go 0.55 times 0.55. You could just do 0.55 squared all over 0.30 times 0.20. Plug this all into your calculator and you're going to get 5.0. Now on to question C. Determine Kp in terms of Kc for the system. There's a great equation we can use for this, and that is Kp equals Kc times RT to the delta N. Delta N in this equation equals 0, and we know anything raised to the 0 power equals 1. 1 times Kc is just going to give us Kc, so we can get Kp is equal to Kc. We already know our Kc, so we can just say that Kp is equal to 5.0. Now on to question D. This question reads, when the system is cooled from 2000 Kelvin to a lower temperature, 30% of the carbon monoxide is converted back to CO2 gas. Calculate the value of Kc at this lower temperature. So the first thing I did was took 0.55, which is our concentration of carbon monoxide, and I multiplied that by 30%. And I get 0.16 moles carbon monoxide. Now, as you can see, 0.16 moles of carbon monoxide also gives us 0.16 moles of H2O gas because they're in the same ratio, which also means there's 0.16 moles of CO2 and 0.16 moles of H2. So we're going, since this is being converted back to this, we're going to subtract 0.16 moles from both of these and add 0.16 moles to both of these. And I did that as follows. 0.55 minus 0.16 gives me 0.39 for a new concentration of H2O as well as carbon monoxide. I then added that to my H2 concentration to give me a new concentration of 0.36 and did the same for my CO2 to give me 0.46 as my new concentration. Now, very similar to part B, we're going to do products over reactants, so it's going to give me 0.39 squared over top of 0.36 times 0.46. When you plug this all into your calculator, you end up getting 0.92. And lastly, question E. This one takes up a lot of space, so I grabbed a new sheet of paper. The question reads, in a different experiment, 0.5 moles of H2 gas are mixed with 0.5 moles of CO2 gas in a 3-liter reaction vessel at 2000 Kelvin. Calculate the equilibrium concentration in moles per liter of carbon monoxide at this temperature. So, the first thing that I did was set up an ice chart. Excuse me while I set that up. So, we have 0.5 moles, 0.5 moles, 0 moles, and 0 moles. Now, we're going to let X be equal to the number of moles reacting. Usually, molarities get plugged into here, but since we don't know the molarities of this, that's what we're trying to figure out, we're going to divide all of this by 3 liters. And here, trying to figure out the moles, we're going to add X, also divide by 3, add X, and also divide by 3. And over here, since we added X, we're going to have to subtract X from our products, or from our reactants. So we get 0.5 minus X divided by 3, 0.5 minus X divided by 3. And for our final, we get X divided by 3, X divided by 3, 0.5 minus X divided by 3, and 0.5 minus X divided by 3. So we're going to set this up very similar in our Kc expression, and it ends up being X squared divided by 9 over 0.5 minus X divided by 3 squared. So we get X squared divided by 9. When we distribute this, we get 0.5 minus X squared divided by 9. Obviously, our 9's cancel out, and we are left with X squared. I forgot to mention, sorry, that this all equals 5, which is what our Kc is equal to. We get 0.5 minus X squared equals 5. We're going to take the square root of this and the square root of this. We also have to take the square root of that. And we end up with X over 0.5 minus X equals 2.2. Multiply both sides by 0.5 minus X. When we distribute, we get X is equal to 1.1 minus 2.2X. Add 2.2X to both sides. I'm going to move up here. We get 3.2X equals 1.1. Divide both sides to get X by itself. And we get the X, which is our number of moles reacting, equals 0.34. Now, since we're trying to find CO, we're going to divide that by our 3 liters. And we get, for our final answer, which I'll write up here so you can see it, very bold, we get 0.11 moles per liter of carbon monoxide. Thank you for watching my tutorial on the 1995 AP Chemistry Free Response question number 1. I hope it helped you a lot. And I also want to give my 9-year-old sister Andy a shout out for helping me record this whole thing. Thanks, And.